So let's take a look at the definition of a logarithm. If we take log base 3, 9, and wonder what that equal to. Well, we're wondering what power must we raise the base to equal the thing we're logging. So we know that 3 squared is equal to 9. So what power must we raise 3 to equal 9? The answer is 2. We can always check that on the graphing calculator. Let's take a look at another example. Log base 2, 8 equals. Well, what power do we have to raise 2 to equal 8? Well, that's cubed, so we know the answer is simply 3. So let's take a look at general form. Log base b of a is equal to c. We know that we can change from log form to exponential form. We know a is equal to b to the exponent c. Geometrically, b slides across, becomes c's base, and the log goes away. So we have log form and we have exponential form. We're going to be using this rule many times. So let's take a look at another example. Log base 2 16 equals. Well, we can answer it the way we did before. What power do we have to raise 2 to equal 16? Well, we know the answer is 4, but we're going to learn a method. Arbitrarily set the log equal to a variable like x. Now change to exponential form. The thing you're logging equals the base to the other side. And we know 16 is 2 to the 4, change of base, last chapter. And we know the bases are the same, therefore we can make the exponents equal to each other. Let's take a look at another example. Log base a half of 16. We want to know what that equals. Well, let's arbitrarily set it equal to x, and let's perform change of base. Excuse me, let's change to exponential form. So I know the base, the thing you're logging, is equal to the base to the other side. Now, I have a 16 and a 1/2, so from last chapter we learned change of base. They both have base 2. 16 is 2 to the 4. 1/2 is 2 to the negative 1. On the right-hand side, we can multiply the exponents together. And then I have the same base, so I can make the exponents equal to each other. Now, if I divide by negative 1, x is equal to negative 4. And again, always feel free to check with your graphing calculator. Okay, let's take a look at some more logarithmic equations. So let's take log base 4 of x. Log base 4 of x equals 3. Well, now the variable is in the place of the log. Again, we're going to change from logarithmic form to exponential form. The thing you're logging equals the base to the other side. And 4 cubed is simply 64. Let's take another example with an interesting step. Log base 5x equals negative 2. So again, I'm going to change to exponential form. The thing you're logging equals the base to the other side. And if I have negative exponents, I bring the thing to the bottom and make the exponent positive. and I know x is equal to 1 over 25. Again, you can check that with your graphing calculator. So now let's see what happens when we have a base of x. So log base x 64 equals 3. So again, let's change to exponential form. 64 equals the base to the other side. Now last chapter we learned if I have a variable with an exponent, I simply want to take both sides to the reciprocal of that exponent. And I do that because 3 times 1/3 is 1, and that eliminates the exponents. So I'm going to mirror this equation. So x is now equal to 64 to the 1/3. Now let's work on 64 to the 1/3. So 64 to the 1/3, well, we have the rule x to the m over n is equal to the nth root of x to the m. So 64 to the 1/3 is simply the cube root of 64 to the 1. Now that 1 is unnecessary. So I can replace the right-hand side with the cube root of 64. And I know that the cube root of 64 is 4. Again, feel free to check your answer. So I'm going to do another example where we see the reciprocal exponent. So let's take log base x 27 equals 3 over 2. So I'm going to change to exponential form. So 27 is equal to the base to the other side. Now again, I have a variable with an exponent. I want to take both sides to the reciprocal exponent of the variable. And the reciprocal of 3/2 is 2/3. And the reason why I did that, because when I multiply those together, the exponents go away. So now I'm going to mirror it again. So x equals 27 to the 2/3. Now again, I can apply the same rule I did in the last question, changing from a fractional exponent to radical form. So x equals the cube root of 27 squared. Now this is a complicated looking thing. Let's take it off to the right. So the cube root of 27 squared. Well, shall I do the squared first or should I do the cube root first? Well, I don't know what 27 squared is, but I do know that the cube root of 27 is 3. And 3 squared is 9. Therefore, x equals 9. Okay, let's take a look at another example. Log base 2 of x minus 5 equals 3. Well, I know that the thing I'm logging equals the base to the other side. And 2 cubed is 8. And if I add 5 to both sides, x equals 13. I could check my answer. And you will notice in the notes, I've started to state restrictions off to the right. We're going to be doing a whole page on restrictions in the next section. So that is when I will be going over that. So let's take a look at another example, a little bit more interesting. Let's go for log, and this time we're going to have a binomial in the base, x minus 2 of 1 equals 2. Well, I know the thing I'm logging is equal to the base to the other side. Now, I know this may look simple and you may usually not forget this, but a binomial squared means we have to multiply them together. I'm going to do this quickly. X squared minus 2x is minus 4x plus 4. So now I can take that answer and I can bring it back in. The reason why I do that stuff off to the right is so I can take it out of the question and it's less confusing for me and I don't make silly mistakes as much. If I subtract 1 from both sides, 4 minus 1 is positive 3. Then I can factor two numbers that multiply to get 3 and add to get negative 4 are negative 3 and negative 1. Then I can solve the equation x equals 3 and x equals 1. Now again, on the next section we're going to go into logarithmic restrictions, but at this point I know that x cannot equal to 3. Feel free to further read the notes and go ahead onto restrictions and then go back to the notes to make sure that's all good. So one final note on when working with logarithms. Let's say log base 2 of 16 is equal to x plus 2. So I know the thing I'm logging is equal to the base to the other side. I know 16 is 2 to the 4, performing change of base from last chapter, and now I have the same base, so I can simply make my exponents equal to each other. And if I subtract 2 from both sides, I know x is equal to 2. One final note,